Right, I'm going to continue the discussion for closed loop transfer function and use this example to show further the effect of the closed loop transfer function or closed loop control on the system behavior, in particular on the poles, how the control introduced through the feedback affect the pole locations. Okay, so on this diagram, what I have here, again, is the simplest feedback control we could have. Now this time, my GS is 1 over S times S plus 8. K is a simple gain, so there's no transfer function, just a scalar value. Okay, but we don't know the value yet. HS is a feedback transfer function, which is 0.8. What I like to do is actually to study how different values of k, if we choose different values of k, how that would affect the closed loop poles. Now in open loop, we only have two poles. If we equate the denominator terms of GS to 0, that will give us two open loop poles, S equal to 0, S equal to minus 8. Now what we want to do is to first of all to derive the closed loop transfer function with k as a variable there, and then see how the poles of the closed loop system will change if we set k to 0, 35, 60, 80, and 160, and so on, so that we can actually see the movement of closed loop poles. Okay, the open loop poles won't change because that's GS, defined by GS. The only thing that we are looking at will be the closed loop poles, see how they change. So first step, to derive the transfer function. Now we remember the second method I introduced for deriving the closed loop transfer function. Say this time, I'm trying to derive the transfer function between the overall input Rs and the output Ys. So in the numerator, it will be the product of all transfer functions in the forward path. So forward path from input to output, so it goes through this k and goes through this GS, and then you get there. So in the numerator of the closed loop transfer function, you will only have k times g. In the denominator, it is 1 plus the product of all the terms in the feedback loop. So over here, we have a feedback loop, so there are 3 terms there, that's k, g, h. Therefore, my closed loop transfer function is k times g, that's in the numerator. These are the product of terms in the feed forward path. In the denominator, we have 1 plus k times g times h. These 3 terms are all in the feedback loop. Okay. Substitute g and k into this. Okay. If you substitute this one in there, I'll get k over s times s plus 8. I get 1 plus k times, k over s plus times s plus 8, and then times 0.2, which is the transfer function of hs. Now again, we need to simplify that. We need to get rid of the fractions, but inside fractions. So this time, I'm going to multiply s times s plus 8 over s times s plus 8. That's really haven't changed anything. That's same term in the numerator, same term in the denominator, and that equals to 1. But the reason I'm doing it is trying to cancel this denominator. I'm trying to cancel this denominator. Okay, so the numerator here cancels that out. So on the numerator, I only have a k left. Numerator there times 1, that's s squared plus 8s. That's s squared plus x. And this term times the second term in the denominator, you cancel that out. So the only thing you got left is 0.2 times k. So that's 0.2 times k. Now if we look at the DC gain from there, now remember, to find the DC gain of any transfer function, you set s's to 0. So this s equal to 0, this s equal to 0, that's k over 0.2k. K divided by 0.2k, that's 5. So the DC gain of the closed loop system is actually independent of k. Okay? Although the closed loop feedback has a role in changing the DC gain from open loop to closed loop, but actually setting the value of k, it doesn't really matter. What value you use really doesn't matter. To find the poles for the closed loop transfer function, I need to equate the denominator terms s squared plus 8s plus 0.2k. Set this to 0. That gives us the characteristic equation as shown in equation 3. Solving this quadratic equation, that will give me a pair of poles, or two poles, -4 plus minus square root 16 minus 0.2k. So it is again, poles actually, for the closed loop, actually is dependent on the value of k. So you get different poles depending on what k value or the control gain you select. Okay. The open loop, you have s equals to 0, s equals to minus 8, so two poles. But the closed loop system, the poles will be dependent on the value of k. There are no zeros because we can't find any s value to make the numerator to 0. Okay, so for the closed loop system here, there are no zeros. Like the open loop in this case as well, there are no zeros. So that gives us the equation number 4. So if I copy the equation number 4 over, this will give me the poles. Now if I set k to 0, this second term becomes 0 in equation 4. Square root 16, that's 4. Minus 4 plus 4, that's 0. Minus 4 minus 4, that's minus 8. So when k equals to 0, I have two poles, minus 8 and 0. Now that's the same as the case for the open loop. But that also makes sense because now when I set k to 0, I've got no control. There's no closed loop control because you set the gain to 0. It basically blocks or cut off the feedback loop. So the poles don't change. If I increase the gain to 35, if I change the gain k value from 0 to 35, that becomes 0.2 times 35, that's 7. 16 minus 7, that's 3. Sorry, 16 minus 7 is 9. Square root 9 is 3. So it becomes minus 4 plus 3, that gives me minus 1. Minus 3 minus 3. Sorry, minus 4 minus 3, that gives me minus 7. So I have two poles here, minus 7, minus 1. Okay, so this pole, the point minus 8 pole from the open loop, moves slightly towards the right. But this one, the 0 pole, moves to minus 1. So you actually, if you visualize it, it moves towards left-hand side. So the system changes from the marginally stable system to the stable system. Increase that further. If I increase the k value from 35 to 60, now 0.3 minus 60, that gives me 12. 16 minus 12, that's 4. Square root of 4, that's 2. So minus 4 plus 2, that gives me minus 2. Minus 4 minus 2, that gives me minus 6. Right? So now I have 2 poles, one at minus 6, the other one at minus 2. Now this one becomes less negative, but this one becomes more negative. Increase that further from 60 to 80. I'm not going to go back there, but you end up basically 80 times 0.2, that's 16. So 16 cancels 16 out. I have 2 poles, minus 4 and minus 4. They are the same. It's a second order system, you have 2 poles. Okay, they may be at the same position, but they are 2 poles. Go down any further from 18, for example, to 160, you will get now the poles will become complex numbers. Not only you have a real part, minus 4, but you will also have imaginary part. But they come in pairs. Okay? The imaginary part will have different opposite signs for the 2 poles. Increase that to 251. This becomes minus 4 plus J6. The other one becomes minus 4 minus J6. And so on. If you increase again further, again, the real part doesn't change because the real part of the pole is not dependent on the value of k. It's only this second part. Once it becomes an imaginary number, then all depend. It's all the imaginary part will be dependent on the value of k. Okay, so this is how the poles of this particular system can be affected by the different values of k. Now remember, we said that the system doesn't actually, the closed-loop system actually changes the dz gain, but dz gain remains constant in the closed-loop case. Look at how they move about as I increase k. Okay, so start from k equal to 0. This is where I have 2 poles, 0 and minus 8. So it's 0 here, that's 1 pole. Minus 8, that's second pole. Okay, that's the same as the open loop poles. As I increase the k value to 35, the pole, this 0 moves to here, this minus 8 moves to there in yellow. Go further to 60. When k value becomes 60, this minus 7 moves to minus 6. This minus 1 moves to minus 2. If I increase that to 80, this one moves to minus 4. This one is also moved to minus 4. Increase that any further, 160. K equals to 160. This moves to here. The other pole moves to there. And if you increase further, this one will keep moving up. The other pole will keep moving down. So you can see the general trend here. The 2 poles, as I increase the k value, the 2 poles will move one towards the right-hand side, one towards the left-hand side, in the middle between the 2 poles. And then afterwards, if you increase the k value any further, one will shoot up, going up, one will go down. I will follow that path. And so basically, the effect of a closed-loop system in this particular case has change the poles. If I change the value of k continuously, this movement will become a continuous. Okay, so but they are essentially moving towards each other, and then one goes up, one goes down. Now, this kind of study that we will be looking at later stage called Lucas approach, basically to see how the closed-loop poles are moved by different value of k. Okay, but we will look into further into this. But in the meantime, just have a think about this. See, and compare the open loop with 2 poles there and all the possible closed-loop poles, as I put the crosses here in color. All the other possibilities with different k's. because k can be any value between 0 to infinite, so the possibilities for closed-loop poles are infinite. But they follow certain paths. They not just appear at any random location. They follow the path infinite in the way that it has to stay on that line, it has to stay on that line. Okay? But it's possible to, for example, in this case, make system more stable because open loop is actually marginally stable. We have this s equals to 0. It sits on the imaginary axis. Okay? And it makes system response faster because as we move this pole slowly towards the left-hand side, the system becomes faster and faster. Remember, the more negative poles give us fast response. Although this pole tend to move towards the right-hand side, the dominant, the slow one is on this side. So it's important to move that slow pole to the left, further left. Now, of course, in life, we don't always have easy life like that, where you only have to deal with a single feedback loop. Sometimes we have multiple loops, several feedbacks required to achieve the control aims as we set. Okay, sometimes a single loop is enough, sometimes it may not be enough. So in this case, on this slide, what I have here is a two-stage control. I have a GS, which is the object for control. That's my plant or the process. I feed this back to here. And then there's a controller here called K2 to try to control the behavior of GS. And then I also feed this back through another transfer function measurement and take that compared with the overall input. The difference between these two is fed into a second controller, or the first controller, if we call that second. Okay? The output there is then compared with the feedback. So there are two feedback loops here. There's one feedback loop, then there's another feedback loop. Now, to derive the transfer function for the overall system, the previous rule I said before will still apply. It's just that you need to apply that twice. Okay, it's not a simple case where you only do it once, like what we had before. So in this case, if my GS is 1 over 8s plus 8, HS equals to 1 over s, and K1 equals to 3, K2 equals to 8. And let's see how we derive the transfer function for, say, for example, from RS to RS. Okay? To do this, I'm going to look at the feedback closed loop that's inside first. Okay, so on the top block diagram, if you look at it, I actually put a square or rectangular shape here. But if you just focus on the inside of this rectangular shape, this is what we have on the left bottom. Okay, there's K2, there's G, there's feedback. Input is U1. Input is U1. Output is Y. Now, this is familiar to us. Okay, if I want to derive the transfer function from U1 to Y1, all I need to do is to say, right, in the feed forward path from U1 to Y, it's K2 times G. So I'm going to put that in the numerator. In the feedback loop, also I have two terms. Okay, because this is unit gain, there's no H here. Okay, so it's 1 plus K2 times G as well. Say the transfer function here is GIN, it's inside loop. Now, once I derive the transfer function from U1 and Y, I can replace this red block, can replace everything inside with a single block or single transfer function. That's GIN that I worked out in my step number 1. Now once you get here, now again, that's a block diagram we have practiced. Okay, so input is R, which is the same as this. Then I have K1, so I copy the K1 here. H, I copy the H here. Okay, just the only thing that I will replace is that block. That block that I'm replacing that with GIN, because in step 1 I worked out the transfer function for that block. Okay, so the transfer function from R to Y will be forward pass K1 times GIN, K1 times GIN in the feed forward or in the numerator. Feedback loop, I have 3 terms, K1, GIN, H. So that's 1 plus K1, GIN, and H. Okay, so do this in 2 steps. Okay, for every step we apply the same approach as we said before. In the numerator, you identify what is in the feed forward pass, multiply all the transfer functions together. In the feedback loop, you identify how many transfer functions there, multiply them together, and then plus 1, put that in the denominator. Okay, so we end up with 2 equations here. The GIN, that's it. That's that little block inside. We have GCL, that's the overall transfer function. Okay, so I'm going to replace everything in GIN first. K2 we know is 8. G is 1 over S plus 8, so 8 times 1 over S plus 8. At the bottom is 1 plus K2, that's 8. G is 1 over S plus 8. Multiply S plus 8 to numerator and the denominator at the same time. And then in the numerator, I end up with 8. In the denominator, I have S plus 8 plus 8, that's S plus 16. So GN, that's the transfer function of that red block, equals to 8 over S plus 16, as shown in equation 2. Once I got GIN, now I'm ready to work out the overall closed-loop transfer function. So K1 is 3. GIN, that's 8 over S plus 8, that's 8 over plus S plus 8, 16, sorry. 1 plus K1 is 3. GIN is 8 over S plus 16. Then times H. H is 1 over S. Okay, it represents an integrator. And then I'm going to try to simplify that fraction inside a fraction. We've done that quite a few times. All we need to do now is actually multiply S and S plus 16 to the numerator and the denominator. So on the top, because we are multiplying S plus times S plus 16, so S plus 16 cancel that S plus 16 out, but we still have an S left. So that will be 3 times 8, that's 4, and with an S left. So on the top, I have an S. At the bottom, if I multiply S and S plus 16 to 1, that gives me S squared plus 16S. And then if I multiply the same term to the second term here, it will cancel this S out, cancel that S plus 16 out, so I end up with 24. Okay, so that's a process where you have to try to find a closed loop transfer function of multiple loops. Try to work from inside towards outside. Now the example I gave here is actually for 2 loops, but you could have 3 loops. It really doesn't matter. Okay, just work gradually from inside towards outside. Look for the blocks that you can deal with. You know how to deal with. Okay. Now sometimes we can also have more than one input. Now, how am I going to derive the transfer function for things like that if you have multiple inputs or multiple outputs? I'm just giving this example to show how we deal with things like that. Remember, we are dealing with linear systems here. So the principle of superposition applies. That means the output can equals to the transfer function from R to Y, then times Rs. Then add the transfer function from ds to ys, then times ds. So we actually work out two transfer functions separately, and then add the outputs together. Okay, so the first step, what you do is, first step, you pretend that ds didn't exist. Okay, so forget about that ds first. Just focus on the rest of it. Okay, so to work out the transfer function between r and y, I have in the forward parts, I have three terms here. 1, 2, 3. So in the numerator, just k times g1, g2. In the denominator, I have a closed loop. There are 4 terms there. So it's 1 plus k times g1, g2 times h. Now that's the transfer function between r and y. Therefore, this part of output y equal to that transfer function times input. That's stage number 1. Stage number 2 is you forget about this. Okay, focus on this ds as the input. Okay, so this time, from the input to the output, the forward path follows the arrows. I only have one term, g2 here, so that's a g2. In the denominator, I have a single loop in the system, so the denominator terms are the same as the one before. So it's 1 plus k g1 g2 h. Now this is the transfer function between ds and ys. So the transfer function times the input equals output. Now this is the part of the output due to this ds. Okay, add the two together. I have two inputs, add the two together. That will give you the overall output. Now, examples like that are quite common in control design and control analysis, because if you have a problem where you want the plant to follow a certain required output, okay, to give you want this RS is close to input as much as possible, so you have the control mechanism here. But then any plant will have disturbances, the factors outside your control. It's not something you can control it with. And we call them disturbance. Like you drive a car along the road, there's a side wind, try to blow you off the road. Okay? It's something you can't control, but you have to react to the result of that. So the disturbance will be modeled in this way. They act on your plant directly. Okay, so it's quite often we have to deal with problems like that. Okay, so I'll set an example for you, or a practice question for you to do as well. For this block diagram, we have two loops here. Okay, there's an inside loop from U to G, and then going back, there's K2. There's disturbance there, there's input there. Okay, and the transfer functions of G, K1, K2, H are all given there. What I'd like you to do is actually derive the transfer functions from R to Y, from R to E, from D to Y, from D to E. Okay? Thank you.